The next topic is the discrete-time Fourier transform, the DTFT. So this applies to non-periodic sequences, or sometimes called aperiodic sequences. Aperiodic discrete-time sequence x of n, then we can write as the Fourier transform capital X of omega. It is equal to the sum from n equal minus infinity to infinity of x of n e to the minus j omega n. So this is the discrete-time Fourier transform. We can also find the inverse transform. So we can go from x of omega back to x of n. It is 1 over 2 pi, the integral over any 2 pi interval of x of omega e to the j n omega d omega. So this is the inverse discrete-time Fourier transform. And so sometimes we'll see this notation, x of n and capital X of omega form a transform pair. Couple notes here, in particular with differences with regard to the Fourier series, where we were dealing with a periodic sequence, and our summation was only over an n0 interval, where n0 was the period of the waveform. And here we're dealing with a non-periodic or aperiodic sequence, so our sum in computing the transform runs from minus infinity to infinity. And then also the inverse transform is an integral. X of omega here is a continuous function of omega. Actually, let me just write that down as a couple of notes to keep in mind here. One, x of omega is a continuous function of omega. A second note is that, and you can show this from the definition, x of omega is periodic, and omega with a period of 2 pi. So it is a complex function, but for a real sequence x of n, which is all we'll work with in this course, then the magnitude spectrum or amplitude spectrum has even symmetry and the phase spectrum has odd symmetry, about omega equal 0. Because this function is periodic, it is typically either sketched over the interval from minus pi to pi, or occasionally from 0 to 2 pi. You'll see both intervals used quite frequently. In the next video, we'll look at a couple of examples of computing discrete-time Fourier transforms.